So, my presentation today is how I won the APL Forge. Plainly. Now, this title comes from Brian. He came up with the great idea, and I love the pun. So, I should say that the antenna that I put on my house is just a Raspberry Pi and this. This is just a little dongle. So it's not anything fancy or anything like that. It's just quite literally that. So, who am I? So my name is Holden Hoover. I am a high school student. I just started grade 12, my final year, just less than 2 weeks ago, actually. And I'm planning to study some sort of computer science in university. So I started APL back in April of 2020 after being introduced to it by Robert Bernicki right there. I was pretty instantly hooked because it seemed like a puzzle, and I really love puzzles. So I love solving puzzles, everything to do with puzzles. I love puzzles. So in the summer of 2021, Bob Bernicki asked if I could do some work on the Apex compiler to implement a Julia backend, which I really enjoyed. And it was really interesting because I think that really helped kind of get from the beginner level of APL knowledge to the intermediate level, which was really, really fun. And then, so some context about planes. I like planes a lot. There's me flying a plane right there. And so I'm very much so an aviation enthusiast. I really like planes. And I do fly planes on occasion. And one such occasion will actually be this coming weekend, where I'll be flying a glider with my local air cadets. So hopefully, weather permitting, I will be doing that. So my project. The project is called Radar Ingest System, and it's an application that aggregates, processes, and stores airplane tracking, which is called ADS-B messages, from a network of individual and independent feeder antennas, with the goal to create a unified database across the network. So I wrote this project actually just in a couple of days of free time that I had in between my maths and physics exam last June. So it was a bit of a rush, but I thought, hey, why don't I submit it? So, and it had been something that I've been sitting on for quite a while because I really wanted to write this in APL. I tried doing it in JavaScript, and that was about 3 months of work to try to do it in JavaScript, and it didn't even work. So, and this was about 3 days, and it did work. So I'm pretty happy with it. So ADS-B, what exactly is it? So ADS-B is Automatic Dependent Surveillance Broadcast. So, automatic. It means that no request is made for the data. The messages are sent out by the airplane automatically at a set standardized interval. So, it's standardized. So it might be 10 milliseconds it sends out its position message or its identification message or whatever. But it's not, the ATC doesn't have to say, hey, who are you? It automatically sends that out. It's dependent. So the systems are on the plane. It's dependent on the aircraft's internal systems to determine its position, its identification, all that. And that's typically using GPS, but it can be done through compass or other means as long as it's digital. The important part is that the ground does not calculate the plane's position. There's an asterisk on that, which is that none of this data is encrypted. And so, I'm sure you can imagine if this data is not encrypted, someone could spoof and say that there's a plane right over my head right now, but there actually isn't. And so, governments and air traffic control, they do have things in place to validate this data, and it's using multiple antennas and using triangulation and stuff to make sure that this is actually coming from where it says it's coming from. And then it is surveillance. So the system provides data to support air traffic surveillance and situational awareness. And then it's broadcast, which I think is really one of the most important parts and the most integral part of this project, is that it's a broadcast. So the aircraft continuously broadcasts its position and other data received by ADS-B, equipped ground station and other aircraft in the vicinity. So it's equipped in the vast majority of planes, and mandates are being introduced to require planes to be capable of doing ADS-B. So it's basically the future of air traffic control, I'd say. And it's used by ATC to monitor planes. And I think the broadcast is the most important part of all, because I wouldn't be able to pick up the signal if it was on some encrypted channel. I wouldn't be able to, this project wouldn't exist, right? So it's quite important. So how does it work in a nutshell? The plane has a computer. And that computer can access all of the needed information, such as the altitude, the speed, the heading. And this computer also has an antenna to broadcast these messages out to the world. So the computer broadcasts the message over the radio. That's typically via 1090 megahertz, which is the frequency. And then there are also various message types, such as position, identification, and velocities, and many more. And the way to decode the data encoded in the messages depends on the message type. So the payload will differ, and the way you can decode that payload does differ depending on the message type. And so then the message is received by an antenna. This could be an antenna on the ground, but it could also be another plane or a satellite. If a plane's in the middle of the Atlantic Ocean, chances are there's not too many antennas on the ground there. But for my purposes, it's on the ground. I don't have satellites in the sky at my disposal. So this is where the Radar Ingest System comes in. So how does the Radar Ingest System work? Well, it has a radar antenna which connects to the Radar Ingest System. Over here is a photo of my friend's radar setup. He lives in the Azores in Portugal. And so he has this box with a Raspberry Pi, and then he has this little software-defined radio dongle there. And then coming out of that, he goes to an antenna outside. For me, I'm a little bit more basic. I just have a Raspberry Pi with this little dongle plugged in, and it goes in my bedroom window. So he's got a little bit of a fancier system going on, and he's got a real antenna. I just kind of use this little setup. But I can still get pretty good range. I can get range of probably around 200 nautical miles, which is fairly good. So I think before I show a demo, it would be very helpful to go over what this is doing. So it connects to the system, and so when a radar connects to the server, it doesn't actually send any registration data, which can be difficult because it's sometimes helpful to have to know where this antenna is to be able to calculate the position of the plane, because the plane, it doesn't send out its actual position. It says, well, I'm sort of over here. And then it sends another message that says, well, I'm actually sort of over here. And then using those two messages, you can kind of figure out pretty accurately where it is. But if you have the where the actual antenna is, of where you're picking up that signal, you can figure it out with just one message, where the plane actually is. So the Radar Ingest System can act as a server or as a client, which I think is sometimes really helpful, especially when debugging. And the radar can also act as a server or as a client. And this means that the server can both listen for connections and connect to individual radars. In most cases, though, the system does act as a server, and the radars connect to the server to feed their data. So that's quite an integral part. And then the radar receives a message. So obviously the radar, now the antenna, picks up a signal from a plane, and so it receives a message, and then the radar sends that message to the Radar Ingest System over the network. So then the radar doesn't actually check anything. It's literally just forwarding the message. Whatever it gets, it's not checking if it's a valid message. It's not checking anything. And that code is not my code. So, but I think eventually maybe it could be, but it's just some code that it's written in C, I believe, and it interacts with the software-defined radio. Ideally, I think it would be really cool to have some sort of code written in APL to do that. So that's kind of a future idea for sure. And then the Radar Ingest System will ingest the message. So I'm going to move on to a little bit of a demo, but I'm a little bit scared of a demo. Oh, right. And then, of course, the Radar Ingest System, after it ingests the message, it creates an entry into a database of all the planes that it can see currently. So yeah, I'm a little bit scared of live demos, so I'm not going to do an actual live demo. I decided after yesterday that it might be a better idea to try to do a recorded demo, just in case. So I've got this little video here. So here's me starting up. I use Cider as the project manager, which I find really helpful. And so I open it up, and then the Radar Ingest System is actually just a class. So if I go here, I create a new class. with the port that I want to listen on, and then I start it and I copy the API key right here. So that will be used for the web user interface. And then what I'm doing actually right now in the background is I'm going to plug in my 2 radars that I have. So it takes me a couple of seconds to run to get the plug plugged in. But once that's plugged in, they'll start feeding this Radar Ingest System, and I'll, in theory, move towards a map in a couple of seconds. There we go, map. So here's a map. And currently, I only have 2 antennas hooked up to it, and one of them isn't picking up anything in this map, but we'll see later that it does indeed aggregate the data. But so there's 2 planes currently being tracked. One is a Delta plane, and one is a United Airlines plane. And so I can select the plane, and it shows up stuff on the top header there. And then what I do here, and then I have an admin panel here, which shows the current radars connected and the total messages from each radar and all of that information, which I find helpful, especially with debugging. So in this video here, I can show that there are indeed 2 radars connected feeding messages. So I have my friend's radar here in Portugal, and he's feeding me the Radar Ingest System. And so he has a plane there. And then I also have my radar in Nova Scotia, Canada, where I have 1 plane there. I also have a satellite view map, which uses an API key from a platform called Mapbox. And so what I do there is I just parse a thing from a file for the API key. So I have 2 planes there, and it does aggregate, and it's all real time. So it's updating in real time, the planes, which I think is kind of neat to be able to see, oh, the plane is right there, and you can see the last updated messages over there, and it has all of this really neat information, which is kind of cool. None of the information is actually historic, though. It's all only real time right now, but I think historic information would be fairly easy to implement. So moving on, I can stop the Radar Ingest System right here. So I run ris.stop, so I stop the server. And then I can also view the database, which I call buffer, but that's kind of a misnomer. And so I have a header defined. And this database here is not actually very human readable. It's fairly, it doesn't really make much sense. It's mostly just so that I can calculate the things that I need to insert the data. It's really not something that a human would ever want to read. So what exactly is ingestion? So I said this word ingestion a lot. So what happens with ingestion is the message first gets sent to the radar. And so then what happens is the message gets cleaned up. So you can see a list of messages, that was a screenshot I took of a bunch of messages that were coming into the Radar Ingest System at one point. So you can see there's longer messages and there's shorter messages. And the shorter messages are technically valid messages, but they're not what I'm looking for. So I'm going to pretend they don't exist. So I'm only looking for the longer messages that start with 8D. And those are 112 bits long. And then also in the cleanup step, I remove the star at the front and the semicolon at the end. And so then the message is sent to a function called ADSB process. This does some more cleaning up and some parsing of the message to figure out if it's a valid message, such as if it's a corrupted message, we want to throw that out, obviously, because I don't want to have a corrupted message. And the ADSB process will check what type it is, so whether it's a position message, a velocity message, all of those various things. And then what happens in ADSB process is once it knows the type of the message, it will send it on to another function, whether it be calculate ground position, calculate velocities, calculate something like that. It'll send that message on to another function, which will then return an aircraft record, which will then return it to the Radar Ingest System instance. And so then that record is added into the database, or it's merged into the database, or whatever, whether it's a new aircraft or an existing aircraft in the database. So I think it would be helpful to look at just one message here. What's the actual path here? So I'll take an example here, and this is an identity message. So this tells the Radar Ingest System who's talking and what the call sign is, so what flight number it is, and all that stuff. So the first thing that happens is we get the message through Conga, and then Conga runs this function here. It's called client append buffer. And so what's happening in here is I'm getting the radar instance. So I'm getting the what radar sent this message through the Conga object. And so that isn't really used right now because I don't actually have any information from the radar. As I said, I don't have registration from the radar, but that's a future project. And then I do some parsing here. So if it's multi-line, I like to split it apart, tear it apart, and make it individual messages because I can't parse multiple messages at once. And then I also take away the new line there. So then it sends it to this process MSG function. So what happens in there is I get the data, and then I process the data some more. I kind of convert it to a binary. So I convert that hexadecimal up there into a binary, and then I get the first 5 bits, which is the format. So that 8D part is kind of the format. So when the format is 17, it means that it's the long message that I want and not the short mode S, which is the shorter messages that we had in the list earlier. And then the process message is supposed to handle errors, but as you can see, I commented out all of the error handling because I was having issues when I was debugging and multi-threading and stuff. I just wanted it to crash whenever it had an error rather than give me a log. And so then from process message, it sends the message into ADSB process. So from ADSB process, here's ADSB process here, that's a trad fun. And so what I do here is I'm just kind of making sure that the database is all good, and then I do some setup stuff, so I get the downlink format, so that should be 17, and then I get the transponder capabilities, so that's telling me whether it's capable of sending these ADSB messages or whether it's just kind of like a drone or something, just kind of not properly sending them. And then I get this thing here called an ICAO code, which is the plane's identification number. So that's it's a unique identifier for each plane, or I should say each transponder on each plane has its own unique ICAO code. And then I get the message here. So this is the actual payload of the message. And then I get the message type code here. So that's contained in the message itself. And then down here, I do something called, I get the parity bits, which is for checking if the message is corrupted or not. So after that, what I do is I'm actually checking the data for corruption. So I run a calculation on the data. I run some fancy stuff with this is the main important function here, this defun here. And then I get the remainder, and I check that the remainder is equal to the actual parity bits that was included in the message there. And then if it's not valid, I'm supposed to throw an error, but right now I don't. And then I have the database stuff. So this is finding the row or making the row in the database. I don't like the way I do it currently, but I think it was thrown together in that 2-day period, and I just haven't touched it since. And so yeah, it's just some database stuff there. And then here's the main part where I'm selecting which function to run depending on the type code. So in our case, we know that this is an identification message because I specifically chose it out to be an identification message. So it'll run the messages.ident function there, and the DBR is the database row, so that's whether it's a new row or not a new row. It might be a blank row, it might not. It will be a blank row in our case because this instance of Radar Ingest System has never seen any planes before. So inside of messages.ident, we have this function here. And so I get the data and the database row, and then I get the message payload and the type code there. And then I have this thing called map here, which is used for the call sign. So essentially what I'm doing here is I'm mapping all of the characters to an index, which makes it really, really easy to get what the call sign is from the binary, because when I was trying to do this in JavaScript, it was really difficult, at least I found it really difficult to calculate the call sign from the bits that I was given. So this is just a map to each index, to each bit. So then over here, what I'm doing is I'm calculating the category of the plane. So whether it's a large A380 double-decker airliner or a tiny little drone, it has its own category code. And that helps classify, it's called the wake turbulence category of the plane, or how much air it's moving around it, I suppose, is how you could best define it. So and then the category here actually creates an index into a matrix table here called gen cat table, which helps define, like it changes these numbers. This gives us 2 numbers here, this category table, and then that's actually an index into a string table or a character vector table in gen cat table there. So then here I'm mapping the call sign. So what I'm doing here is I'm mapping the indices which are provided in the message payload to the map function here. And so messages are actually fixed length of I believe it's 8 characters, which is helpful. So call signs have a maximum length of 8. And then also here I have the yes, so I'm assigning the call sign and the category into the data here, and then I put it in the database row, the call sign and the category, and then that returns it. That returns it to the Radar Ingest System thing. So I don't actually use this data vector here. I think I had it in there for some reason. I thought maybe it could use it, but then I moved on to using database rows. So probably that's going to come out at some point, but in the meantime, I do just have this database row thing here. And then here's the actual database once it has that message ingested. So you can see here I've got the ICAO code, which is the unique identifier in hexadecimal for the aircraft. And aircraft registered in different countries actually do usually have a unique starting code. And this is a KLM flight that I have from this message here. And then the category code index is 40, which I don't know what that is off the top of my head, but I assume it's some sort of airliner, not a drone probably. So that's what we get from that message. So all of that info there is what's encoded in that message essentially. So the actual architecture of the Radar Ingest System is quite interesting. So I have Cider as the project manager, so that's how I open the project. And I find Cider to be really good. Right now on my laptop, none of Cider and Tata are working, and I'm not quite sure why, but it's something to do with Conga and something to do with my Linux and my new laptop and something. And so Cider and Tata, really helpful for packages, because then I can import Dyalog Jarvis and whatever other packages I intend to use in the future without having to worry about where I'm getting them from. And so I do use a Dyalog class, so that's part of the object-oriented programming, and this is something that I've never used before, so I kind of had to figure that one out, but it's really interesting to try to use object-oriented programming in Dyalog APL. I haven't, I had some interesting problems with it, but I think it all works now, so that's good, and I'm sure I'll be able to kind of finesse it a bit more later. And then I use Dyalog Conga for the actual receiving and the receiving of messages and connecting to the radars available. And then I use Dyalog Jarvis, which is also obviously using Conga in the backend as well, which is used for the web API and the web user interface as well, which the user interface with Dyalog Jarvis, I don't think Jarvis is actually designed to host HTML pages, but that might be just my opinion. And I've never really used Jarvis before, so that's that. But it was quite interesting. Brian, do you have anything?
Yeah, it wasn't designed to host HTML pages. We just kind of made it do it.
Okay, you just kind of made it do it. Yeah, so that's that. I did do it, and it does work, and it kind of looks nice. What I do here is with the HTML page is I actually run I have an HTML file which is like a template, and then I tell APL to insert certain data into that template, and it also has some JavaScript embedded in the HTML page for the map stuff and the automatic reloading, and it has just a web API as well, which is I think is really helpful, because that means that I can access the data in this application with other platforms. So if I had a friend who wanted to write, say, a Discord bot or some other web API application. It can connect into the Radar Ingest System and get that data out of there and then display it somewhere else, which is quite interesting. And then I also have some ideas for the future. So first thing I want to do is figure out the user interface. I like it, but I think it could do better. It kind of looks a bit pushed together, and I'd like to have an emphasis on the user. So I want to have a very robust user interface, and I'd like to maybe integrate it with the new EWC that I've never heard of before this conference, or perhaps something else rather than the way I'm doing it with Jarvis, because I don't want to do something that's not where it's not intended to be used for. And it might also be better to write the user interface in something that's not APL, but I'd rather not have to touch HTML because I don't really like HTML. It kind of makes my brain hurt. Yeah, I don't really know, but I'd like to have a proper user interface probably. And then I'd like to make it faster because I don't think that my code is very optimized in any way. I don't have the numbers because when I'm running this, I run it on my home system, which has like 128 gigabytes of RAM. So I don't experience any issues with it, but it probably isn't very optimized. I also am running it currently with just 2 antennas, which feed probably 100 messages per second. And if I wanted to have a whole world view, I'd need to be able to handle approximately 14,000 messages per second. So there's quite a big number there, and so I'd need to be quite efficient with it. And that number actually comes from a platform that my friend and I made back a couple of years ago called radarplane.com, which is actually the purpose of this application, is to ideally integrate it with that in the future. So make it faster, quite important. And then it needs to be more robust. I really don't know how secure my code is. I feel like there's probably some way to inject something somehow, and someone could figure that out, and it wouldn't be so good. So I'll need to test it a lot more to find the bugs and to ensure that the application is robust enough to handle the thousands of radars that would be feeding it. And then another really big thing here is a new radar communication protocol. So I think it would be really helpful to have a protocol here where written ideally in APL, so that I can run APL on a Raspberry Pi here and feed the Radar Ingest System using APL on both ends. So with Radar Ingest System ingesting the message, and then maybe a radar feeder system feeding the messages. And then I could have my own protocol where I do the registration of the radar and I get the position of the radar and all of that stuff. And it would also be well documented, because the current protocols for sending ADSB messages are quite undocumented. So it's kind of just a guess of, well, I see there's a semicolon here, so that must mean it's the end of the line. But nobody's actually written down what everything means. There's another protocol that's written using some sort of compressed binary, but nobody actually knows how it works. There's like one C application that can do it, and I have no clue. I don't want to read the C to try to figure out what's going on, and I don't really want to try to make an error in how it works. So I think it would be just easier to write a whole new radar communication protocol, maybe using some sort of compressed, or I don't know, something more optimized for the high levels of data that are coming out here, and then I'd be able to have the position of the radar right there. So that's that. That's the Radar Ingest System, really, all in all. Does anyone have any questions?